Hey guys, I'm Moishi from Peking University. I'm glad to present our work about building a runtime system for autonomous camera. It's a collaborative work with Purdue University and Microsoft Research. As we know that video analytics has been powerful and pervasive those days. For example, counting persons in a retailing store can reveal customers' interest and therefore guides the optimization of merchandise arrangements. For sports events, counting people can also help avoid some crowd-related disasters. However, today's video analytics mostly focuses on those urban and residential areas where the camera is wired to electricity supply and has good internet connection for data and computation offloading. Instead, we want to extend the scenarios of video analytics to those rural and off-grid areas. There are a lot of opportunities and applications existing in such diverse and natural environments. For example, on a large cattle farm, cameras can help monitor the cow's movement. In the wilderness, biologists can use camera to count different number of animals and track their behavior. To enable such new scenarios, we propose autonomous camera as a new operation style for intelligent cameras. Autonomous camera has two notable features. The first one is energy independent because it can only operate with harvested energy without connecting to electricity wire. The second one is compute independent because it cannot offload the video data to back-end processing. So here's the typical hardware of autonomous camera. It has a commodity SoC like Raspberry Pi running at a few gigahertz. It also has a chargeable battery so that it can operate at night. The camera is purely powered by harvested energy, typically a small size solar panel, which can harvest about 10 watts hour per day, depending on the location and the season. The camera only has low power long range network connectivity like LoRa, which is designed for IoT devices. So those networks are only capable of sending data at very low bandwidth, such as a few or at most tenths of kbps. So because of this network constraint, the camera only sends concise video summaries to the users, such as video object counts, instead of sending the raw image data, which is very large. To support the operation of autonomous camera, we built a runtime system, AF, which can continuously produce video object counts as the video summary. We target at object counting because it is a key query type in video analytics and has been extensively studied by the computer vision community. And object counting also has abundant use cases in autonomous camera. So to use ELF, a user sends a query to the camera. A query specifies the object type to count and the length of the time window. For example, counting the number of cars in every 30 minutes time window. Then ELF will sample and capture image frames and process them by some neural network, and finally produce object counts for each 30 minutes time window as specified. So here, each count comes with a confidence interval, which makes them meaningful and useful to the users. Giving a confidence level like 95%, a confidence interval has a 95% probability to cover the ground truth. Of course, a smaller CI weight indicates a more confident and accurate result. Based on the counts, users can further answer some high-level statistical queries like what's the probability that the cars in this traffic intersection has doubled since last week? The central problem of ELF is to manage and plan the very limited harvested energy for counting. So here we follow a tradition of priori energy harvesting systems that we must use an amount of energy in a horizon no more than what is given by the solar panel. A horizon here is typically set as 24 hours. Apparently, with such limited energy, the camera cannot afford processing every frame with the state-of-the-art neural network. So the trade-offs may come from two dimensions. The first one is frame sampling, and the second one is neural network selection. So how do we plan the energy to get the overall most confident result? So to be more specific, we set the target as the smallest mean CR weights. So here is an overview of AF's workflow. With a video feed, AF samples frames and selects a neural network to process those frames. So there is an aggregator which will integrate the errors introduced by the frame sampling and the inaccurate neural network into a unified single confidence interval. The decision of how many frames to sample and what neural network to use is made on the fly by a reinforcement learning based planner. For time limit, this talk will focus on the planner component, and you may check out our paper for more details about this error integrator. Let's first look into the action space about what neural network to use and how many frames to sample for this counting task. The left figure shows the CR weights on the different energy consumption with ULV3, which is a very expensive object detector neural network. So of course, more energy leads to more compact, smaller CR weights, as this figure shows, because more energy means we can sample and process more frames. We also tried many other neural networks as candidates, represented as different curves and colors in this figure. So apparently, with a given energy amount we can use, there is a trade-off between sampling more frames and using a more accurate neural network. A key observation of the trade-offs from different neural networks is that there's no silver bullet choice that performs the best at different conditions. So, for example, when the energy consumption is low, cheap neural networks like SSD Inception V2 results in a smaller CR weight. So this is because when the energy is low, the CR is primarily bottlenecked by the inadequacy of frame samples, and because cheap neural networks takes less energy to process per frame, so using cheap neural network allow more frames to sample. But when the energy consumption increases, a more expensive neural network, ULV2, performs better than the previous cheap neural network. And when the energy further increases, the most expensive neural network here, ULV3, becomes the best choice. So this is because with abundant energy, we can afford processing enough frames even with expensive neural network. And the confidence interval the weights starts to be bottlenecked by the errors in the per frame error. We call this front as the bottom left segments from multiple curves as the energy CF front. This front basically contains a combination of all the optimal count actions with different energy consumption. So with this concept, it becomes obvious that AF should always operate on this front to pick the neural network and the number of frames to process, because it always returns the smallest CR weights compared to other decisions. This energy CR front for a given time window can be constructed by the error integrator, as we have mentioned. So this integrator shows that how this front looks like not only depends on the accuracy of the neural network we use, but also depends on the video characteristics, especially the mean and variation of object counts in that window. So as you can imagine, different time windows have different energy CR fronts because they have different contents. So such observation leads us to the second technique of AF, which is planning the energy across different windows to maximize the overall counting accuracy. So, how do we plan the energy across windows? Which window should receive more energy than others? So we first introduce an Oracle planner here, which should perform the best, but is built on an unrealistic assumption that it knows all the energy CI fronts of each time window. So with this unrealistic knowledge, the Oracle planner can solve the problem by iteratively allocating a small energy slice to the time window, which will have the largest CI weight reduction or the benefit. So after each allocation, we need to update the CI and the count action of that window who receives our energy slice. So this process finishes when all energy has been allocated and the final decision becomes the Oracle Planner's output. However, the Oracle Planner is unrealistic as we cannot predict how the videos will look like in the future. But we have to make the decision right now because we need to decide how many frames to capture and to process to deliver the results without delay. To make it happen, we make a learning-based planner which might imitates the Oracle planner. The rationale here is that videos have strong daily and temporal patterns. For example, the car count in a time window is often correlated to the priority windows of the same day or with the same time window of priority days. To deploy, we can collect several days of videos and train this learning-based planner based on the output of the previously mentioned Oracle planner. So after training, the planner can be used for predicting the count actions online. So currently, the neural network selection and the sampling number are predicted in two agents separately. The observations or input of these agents are the knowledge of priority windows and the windows at the same day, the windows of priority days. The reward and the penalty is calculated as the planner's decision deviation from the oracle's decision. To make sure that the planner won't violate the energy model, ELF will reserve some energy for each feature window so that even if ELF misbehave and spends too much energy already, in the future, at least a small number of frames can still be processed to provide a meaningful CI for those time windows. We implement a prototype of ELF on heterogeneous hardware. So here we use Raspberry Pi 4 for processing the frames in a batch mode at the end of each time window. We also have a microcontroller, OpenMV M7, to wake up and capture images with much lower energy cost. The use of microcontroller here is to decouple the image capture and the image processing so that we can keep the Raspberry Pi 4 in sleep at most of the time to reduce the overall system consumption. In fact, our experiments show that if we only use Raspberry Pi, the confidence interval will be much wider because of too much energy wasted on image capture instead of processing. We evaluate our system with over 1,000 hours of public traffic videos. We compare ELF with three baselines. The first one, Golden NN, always use the most accurate model, which is YOLO V3 in our case. And the second one, UniNN, can pick the most efficient neural network, but it's fixed for each video stream. The Oracle is the unrealistic version of ELF with the Oracle Planner as we discussed. So here we use a typical energy consumption range between 10 watts hour per day to 30 watts hour per day as we have measured with a small solar panel. The results show that ELF can produce results with about 11% error on average, And with 95% confidence interval, AF can generate valid confidence intervals with 17% weights. So such results are often good enough to provide useful information to users, comparable to priori query systems, which provide CIs. Compared to the first two baselines, F can significantly reduce the CI weights up to 3.4 times. So this is because F operates on the energy CI fronts only to pick the proper neural network for processing, and globally plans the energy across multiple time windows instead of using a single window across single neural network across different windows. In fact, according to our observations, the count action made by AF about what neural network to use and how many frames to process vary a lot across different windows. AF also achieves similar performance to the Oracle Planner with less than 5% larger CI weights. So this is because our learning-based planner can well imitate the Oracle Planner in selecting the number of frames and the neural network to use, as we have observed. We also tried some AI accelerators like Jetson Nano and HTPU to replace the Raspberry Pi in the AF prototype. So those accelerators can process frames with lower energy costs so that CIs are reduced noticeably. However, even with such hardware, we still cannot afford processing at very high frame rate, so sparse sampling is still needed, and the energy is still a limiting factor which validates AF's key designs. To summarize, we propose a new paradigm for camera operation and deployment, which we call autonomous camera, to expand the geo-frontier of video analytics. We design and implement AF, a runtime system for autonomous camera that can continuously generate object counts with good accuracy. And that's the end of this talk, and please check our paper for more details. Thank you so much for your interest and attention.